Hello and welcome to our Day 2020 virtual series. Today, we are delighted to be with Professor Peter Schlosser from Arizona State University. And he is also the Vice President and Vice Provost of the Julianne Wrigley Global Futures Laboratory at ASU, as well as the Director of the Global Institute of Sustainability and Innovation. Peter, thank you so much for joining us and welcome.
Thank you for having me.
So I'd like to begin today with just a sort of an overview of where you see us within the earth sciences and as they relate to climate. And, right now we know that we're experiencing massive problems as a result of the overpacking the atmosphere with carbon dioxide. And I know that you're an expert in how water relates to that, the hydrological cycles of the earth. Could you give us a brief description of how you see the feedback loops that we've been experiencing in the forms of extreme fires in the West, droughts, the over-acidification of the ocean, et cetera?
Happy to do so. Let me start with the bigger picture. Since centuries, humankind is putting multiple pressures onto the Earth system, on life on the planet and the systems that support life. And that comes in many dimensions. And especially it accelerated since roughly the beginning of the Industrial Revolution. Since that, we feel cascades of acceleration of development. With that development comes increased use of energy. With the increase of energy of mainly fossil origin, so far about 80% today is of fossil origin, we are changing the environment, and here we are looking at the atmosphere. We are actually increasing the greenhouse gases of the atmosphere, mainly through carbon dioxide, which is about 2/3 of the greenhouse gases in the atmosphere. That, of course, led to the well-known effect of what is commonly called global warming, which means that we have actually increased globally the temperature of our planet by roughly 1 degree Celsius so far, about 2 Fahrenheit. Now, a lot of people would say that's a small number. I have day-night temperature changes of 10 times that. We have to put that into context of what happened on long time scales, into the climate context. For example, between an ice age and a warm period, globally averaged, we have about 5 degrees Celsius warming from the ice age to the warm period. So we are already about 20% into that amplitude. We have committed to almost another 1 degree Celsius of warming. That would bring us up in that cycle about 40%. And we are not going back to the natural cycle, which would get us onto a cooling trajectory, but we are actually going from a warm state to an even warmer world. And that is what we are starting to see in many parts of the Earth system. We do have warmer temperatures, which leads to the heat that we feel, heat records. For example, 2019 in Paris, we had heat records of 45 Celsius. That is in an area that is not equipped with the cooling infrastructure. We see wildfires up to Alaska in the high north, through California, the southwest of the US, Brazil. In Brazil, we have to be a little bit careful. It's a combination of climate and land use. But then also in the south, we have Australia, which had a fire inferno. We also see more floods and droughts, and we see melting of ice and thereby increasing sea levels. So what we are experiencing right now is that we are seeing the effects of human intervention with the balance of the Earth system in more places, in more forms, more frequently, and at higher amplitudes. That really should wake us up to the fact that we are not just tinkering around the edges with the Earth system, we are making changes that dramatically change it, that can lead to catastrophes as we are moving forward if we are not recognizing that and very quickly change our course of action.
Thank you. Could you, for that overview, could we safely say that the massive fires that we experienced in the Western United States this year are directly related to this over throughput of greenhouse gases into the Earth's atmosphere?
So it has been projected through the best models that we have since quite a while that the Southwest is getting drier. And we experience that. In addition, of course, the temperature is increasing. The two combined provide for much more fuel for these wildfires. So in that sense, there is a high likelihood that the intensity and the frequency of the wildfires is linked to human-induced climate change.
Mm-hmm. Yeah. I understand that the IPCC report of 2019 suggested that with over 2,000 gigatons of carbon in the atmosphere, 2 trillion tons, that they say that we must begin to pull down, whether through regenerative agriculture or through actually geoengineering, the devices that we have invented to pull out, some say half of the carbon that's up there in order to stabilize to the 350 and then perhaps gradually back down to what was normal for 280 to 300 parts per million. Could you talk a little bit about the work that your team is doing down at ASU along the lines of carbon removal?
Yeah, to your point, we have reached a state where in order to keep the planet below 2 degrees Celsius, hopefully at around 1.5 degrees Celsius warming, which is considered staying out of the zone that typically is called dangerous interference with the climate system, we have to do two things. We have to cut emissions quickly to de facto to close to zero, but we also, and that has to happen within 1 decade, we have to cut the emissions by roughly half. By 2050, we have to be at net zero. We only can get there if we take some of the CO2 back out of the atmosphere. There are several methods to do that. There is what is often called nature-based solutions. It mainly means, or in rough terms, it means to build up biomass on the planet that will take up the CO2 that's in the atmosphere. The other method, and I think we might need both to contribute in almost equal proportions by 2050. The other one is chemically based, often called direct air capture. That means to bind CO2 that's in the atmosphere on adsorbing surfaces, concentrate it, and then release it from these adsorbers in concentrated form and put it away into long-term storage. What we are doing here is an activity that about 3 other entities are also doing, and we are all still in a startup mode, and that is to design devices that can be put into the wind that adsorb the CO2 as the air moves through them, concentrate it on these surfaces, and then release it from the surfaces and put it into a concentrated form, almost pure CO2 that then can be sequestered. Or hopefully some of it can be used for commercial economical purposes. So we have an agreement with a private entity to scale up these extraction units. And that is the work that Klaus Lackner had pioneered more than a decade ago. And the plans are that this then can be scaled so that by 2050, we can extract of the order of 5 to 10 gigatons per year of CO2 back out of the atmosphere.
Fantastic. So there's very, very positive developments on that score. When I was fortunate to attend President Olafur Grimsson's Arctic Circle Summit in Reykjavik, Iceland, I was shown through the Hellisheedy geothermal power plant where they're developing something called CarbFix. And there was some very promising developments in the ability to take the CO2 from the atmosphere, mineralize it onto basalt rock at great depths in the Earth's crust. I wonder if you could comment on that process of sequestration, because it seems to me that no matter how much of the carbon that we can use for, let's say, bicycles or soda pop bottles or anything that we could use carbon for, the majority of what we'll be pulling from the atmosphere will need to be sequestered so that it will never leak out again.
So if we are looking at the amount of CO2 that has to be extracted back out of the atmosphere, several hundred gigatons to maybe 1,000 gigatons, that's a tremendous amount. Of course, we would like to use as much as we can of that CO2 for purposes such as greenhouses, soda, companies, enhanced oil recovery, or synthetic fuel, which is an area of great interest for research right now to see how much we actually could use in such a way. But we have to keep in mind that we never will be able, to the best of our knowledge right now, to put all the CO2 that has to come back out of the atmosphere and put it into a commercial cycle. So quite a bit has to be put away forever. And there are several ways to do that. We can store it on land, which would actually put it into porous media, where it's either reacting or non-reacting, where it fills pore space and is safely sealed. If it reacts, in essence, it becomes part of a rock matrix and is in the lowest energy state and will be there forever. Or we can put it beneath ocean sediments or close to mid-ocean ridges. Now, the mid-ocean ridges brings me to Iceland, because Iceland is part of the mid-ocean ridge. It just is actually elevated out of the water. So it is a basalt formation that can react with CO2, as Carbfix has shown. And the question here is, how much capacity do we have? How easy is the logistics to get the CO2 to mid-ocean ridge basalts that are off Iceland, and how big is the capacity of Iceland itself? So in principle, there is a very promising method to bind CO2 to minerals and thereby put it into the lowest energy state, put it away forever. The questions that are still being researched is, where is the capacity? What does it take logistically to get the CO2 to these places, inject it, and then have it react so that it is bound forever?
Yes, it's my understanding that the Atlantic Rift that goes from North Pole to South Pole has various opportunities for this type of application. But most of that, of course, is under the deep part of the ocean in the Atlantic. And so, but when I was fortunate to go through a tour at the Lamont Doherty laboratories in Colombia, I also met some folks over there that were working on the beginning to work on the Pacific side off of British Columbia with a similar kind of strategy. I wonder though, Peter, do you feel that we're going to have a global price point on carbon in order to facilitate this vast extraction? What will be the driver?
I think in the end, for all the CO2 that we have to put away, that we cannot use commercially, we have to pay a price. And that is, as Klaus Lackner always says, this is similar to a waste disposal project. If we are littering the planet, in this case the atmosphere, with waste, and the CO2 can be looked at as waste, then in order to take care of it, to clean it up, we typically have to pay for it. That's like, how we deal with waste cycles. So in order to store safely, put away for good the CO2 that we have put into the atmosphere in excess, we have to establish a price that it would cost per ton to accomplish that task. And the price is anywhere from a target of maybe $100 per ton at this point to hopefully down to 50, or maybe in the most optimistic scenarios, maybe down to $30 per ton. Now, these are all abstract numbers for somebody who doesn't deal with them all the time. What would it really cost then in terms of, if we would translate that into how much would that be if we would add it to the cost of a gallon of gasoline? And there it would be of the order of 5 to 10 cents. So it's not that this cost would be so big that we cannot stem it in principle, but we have to get to the point where there is the will of society, of decision makers, to say, we have created that problem for us, we have to solve it, we also have to bring up the resources to do so.
Yeah, that's exactly what I was trying to get to. In terms of the hydrological cycles and how they've been impacted with the release of all this carbon. One of my colleagues, Lester Brown, who used to run the Earth Policy Institute, wrote a book recently on water refugees, how cities around the planet are drying up and literally populations are starting to have to move as a result. And I know that this is one of your areas of expertise. Could you comment upon that piece of the interaction?
So a lot of the global water cycle is driven by the ocean and thereby the ocean temperature. So by changing the ocean surface temperature, we are changing the way water moves from the ocean to the continent. Precipitation then turns it into rivers, or it will end up in rivers, and that goes back into the ocean. That's a closed cycle. By changing the distribution of the surface temperature of the ocean, we are actually changing the patterns of the hydrological cycle over land, which means we are changing the flood and drought patterns. So we are experiencing more droughts in some areas and more floods in others. Neither one is actually desirable in itself. But if you are looking at the areas that are drying out, that clearly can lead to the point where we are exhausting our water resources, not just from precipitation, but also from groundwater that increasingly is being tapped to make up for the deficits. And if you reach a critical point, it might mean that you either figure out how to supply water to these areas, or you have to, in essence, move out of these areas. So these are real possibilities that we are facing. And in some areas, we are actually, we can almost see it by satellite now, how we are depleting groundwater. You're just looking at elevation changes of land, and you can see how much groundwater is being withdrawn. We see just by precipitation records how these natural conditions are changing. For example, this year, we had over California and part of Arizona, we had areas where we only received between 5 and 25% of the normal precipitation. That's an area that's already arid. So that really puts severe water stress on the environment. And if we are looking now, a lot of people hope, because we didn't have a monsoon in Arizona this year, the second year in a row in a way. So people are actually looking for the winter precipitation. Sadly, we are in a La Nina condition, which for Arizona means that it's typically dry. So there is no immediate hope that the deficit built up this summer will be made up by excess precipitation in winter. So we are actually seeing more and more situations where we are pushing against boundaries.
Along those lines, the Colorado River Basin supplies the drinking water for some, I think it's 40 million people between Phoenix, Los Angeles, Las Vegas, others. And I guess my question is, given how we're using that water for agriculture and how the water is also being needed for household and industrial uses, do you think that we're going to have to change how we're allocating that particular watershed?
There is, of course, a problem in principle with the Colorado in terms of the supply of water, the quantity of water, because of the snow loads. They are changing too. But even if we would leave that aside for a moment, and we say, what is the distribution between the individual sectors, such as agriculture, industrial use, and household use? A large fraction is actually used of water that we are using as global society is used for agriculture. In order to keep the food production safe, we have to look at new food systems, new irrigation systems. We sometimes planted the wrong, crops in the wrong place in terms of their water use. So we have to optimize which crops we are growing where and how much water we have to deliver in which fashion. So going from aerial irrigation to drip irrigation and in using specific crops that are using less water in drier areas can get us quite a bit of the way towards a more sustainable food production system. But again, this is something that we actually know since quite a while. The response in terms of applying some of our knowledge into action to help ourselves is typically very slow.
Mm-hmm. Yes. Is there a way chemically to separate, back to the CO2 conversation, the carbon and the oxygen molecules? Is that a possibility to help to solve this problem of buildup in the atmosphere?
So once the CO2 is in the atmosphere, it's in the atmosphere. So we just have to get it out by absorbing it on the appropriate surface. What we, of course, can do is, if we want to use some of it, as we mentioned before, we can put these extraction units next to solar energy production. The energy from the solar arrays can be used to split water. If we have hydrogen and CO2, we actually can produce any kind of synthetic fuel. That in itself actually would help to reduce the amount of carbon we have to put away. And in that sense, it would actually be a positive contribution. It would create a new industry. By the way, the extraction of CO2 in itself, to also point out some positive trends, the extraction itself at the level we are talking about, that we have to get to, will create $1 trillion industry. So some of these new ways to produce energy through renewables, to remove some of the CO2 from the atmosphere, will actually create economic opportunities and will create new jobs. So it's not that everything that we are looking at as we are moving into the future is doom and gloom, is sacrifice. There are a lot of opportunities in it. We just have to make different choices. And what is tricky for people, we are all creatures of habit. So we don't like to change in principle, but when it comes to environmental change, we often think these changes mean sacrifice. I would contend that if we are not making these changes, we will see the ultimate sacrifice, because then half a century from now, we are really hitting the wall. And what we really want to have is a future of opportunity, not a future of sacrifice. So we better steer onto that course right now.
Well, in that light, and as we reach the 5-minute mark for the conclusion of our conversation, if you could talk a little bit about the extraordinary work that you and your colleagues are doing at ASU. It's my understanding that each student comes through with some kind of a sustainability emphasis or degree, and that with, I believe, 150,000 students, that's quite a impact that you're making.
Yeah, not quite there yet, but moving towards that. We have about 125,000 students right now. In the fundamental charter of the university, as one of the pillars, is the future of the planet is sustainable outcomes. And that is reflected in some structures, but also in the desire to equip all our students with the basic knowledge of what is the pressure on our planet, what is our planet in general, and how can we move into a future that still has opportunities for these generations to thrive. So that is a fundamental philosophy of the university as a whole. Within that, early on, when Michael Crow became president, he put structures in place that helped that along, like the Global Institute of Sustainability, the School of Sustainability, which was founded in 2006 and in essence has been the first school of sustainability. So that then was driven to the next level by forming the Global Futures Laboratory, which takes all the assets that the university has in that area of thinking about the future in one comprehensive structure. Within that is a large research institute with 30 centers. There is also a new college with 3 schools, the School of Sustainability, the School for the Future of Innovation and Society, and a newly created School of Complex Adaptive Systems to understand the underlying complexity that is probably the unifying theme of thinking about the Earth system and its future. So this vision and pragmatic approach that Michael brought to Arizona State University in 2002 is living on and is being scaled up. And within the college, we want to, within a few years, train about 5,000 students with detailed knowledge about these issues, while we want to make sure that all the other students get a sense of what our planet is, where it came from, what the issues are, and how we can actually create opportunities to keep the planet a place that is not just livable, but that offers opportunities to thrive.
Fantastic. Well, I just want to thank you, Peter Schlosser, Professor of Sustainability and Director of the Wrigley Global's Future Laboratory at ASU, for your leadership, your vision, and for bringing in the next generation of solution-oriented students who will go on into our society and figure out how to solve these problems. Thank you so much for your time today, and I look forward to working with you in the future.
Thank you for having the opportunity to talk about these critical issues.
Okay, thank you, Peter. Thank you.